Welcome back to our Chapter 6 lecture in Probability and Statistics. Okay, so where we left off last time was discussing the different types of errors that we can get in our linear regression modeling. So let's get back to those. So one of the ones that we are going to talk about is an SS sub t, and that is called our total sum of squares. So what that is that measures the variation of the y sub I, or the individual observations, around their mean value of y bar. Next we have an SS sub e, and we talked about this a little bit before. That's called our error sum of squares. And what that does is it describes the variation that's attributable to factors other than the relationship between x and y. And then our SS sub r is called our regression sum of squares. So what that is that explains the variation that we can attribute to the relationship between x and y. So let's look at these formulas, and then we'll look at a visual to help understand them. Okay, so the total variation, or the SS sub t, is made up of two parts. So the SS sub t is equal to my error sum of squares plus my regression sum of squares. So the formula for SS sub t is the difference between each observed value and the mean squared, and all of those added together. The error sum of squares is each residual squared and then all added together. And then my sum of squares regression is going to be the difference between my predicted y value, or the y value on my line, minus my mean y value, quantity squared, all added together. So once again here, I feel like the key is knowing when to do the total summation, or the adding up. So just pay attention to when things are squared and when things are summed. Okay, so here, kind of the legend for this is y bar is my average value of my dependent variable. My dependent variable, y is my observed value, and y hat is the estimated value on the line. Y hat is always on the line. Okay, so let's look at a graphic that, in my opinion, helps visualize this. Okay, so here I have some data point. So that data point has a coordinate, and that coordinate is comprised of an x coordinate and a corresponding y coordinate. So this coordinate is just one of many. I'm just going to deal with the one because it's going to get kind of complicated in a minute with all the formulas on the screen. But this is just one data point among many. With those many data points, I have some line that I put in the middle of all these that I calculate based on my least squares regression that minimizes the sum of my residuals. So here, this is my y hat, or this is the value that is calculated to be the exact middle of all of this data. Based on that line, y hat, I now have this x value that has a predicted value of y hat over here. So this is predicted, this is my actual. So then I have the mean of my y values. So obviously I have other y values down here somewhere that are helping make up this mean. But this green line is then my average for all y values. So then this up here, the distance from my point to my predicted line, is my SSE, or my error sum of squares. So SSE is the difference between my observed value and my predicted value that lies on my line, all quantity squared. My SSR value then, my regression sum of squares, is going to be equal to the predicted value minus my mean value. So that is the distance, or that's the value right here, my SSR. So then in turn, my SST is going to be the distance from my data point to my mean y point. So I hope that kind of helps you see that SST is equal to SSE plus SSR. So one of our most important things to talk about, kind of the ultimate goal of all of this regression analysis, is something called the coefficient of determination. So the coefficient of determination is labeled as r squared, and what it is it's the portion of the total variation that is explained by the variation in the independent variable. So basically that tells you how related your data are. So let's look at that. So the coefficient of determination is also called r squared, and once again is denoted as r squared. I know that sounds redundant, but sometimes it's spelled out, sometimes it's not. So either way it means the same thing. Okay, so the formula for that then is 1 minus my error sum of squares over my total sum of squares. So this ratio then will be somewhere in between 0 and 1. So the closer it is to 1, the more explanation we have of why our model varies. So usually you want it to be close to 1 because you want most of your model, if not something like 99% or 0.99 of your error, to be explained by your model. Okay, so let's look at some values of this. So an r-squared value of 1, let's say we do all that calculating and we get a 1. Then all of my data points would lie exactly on my modeled line or my predicted line. So that would mean it would be a perfect linear relationship between x and y. Okay, so even if it's in the negative direction, it's going to be a positive 1 because the positive 1 just infers the relationship to a linear line. So same thing here, r squared would equal 1 because 100% of the variation in y is explained by the variation in x. That's what that means. Okay, so here, this is showing you how it looks a little bit differently. This is what it looks like to have r squared between 0 and 1. So notice the points aren't exactly on the line, but they're still somewhat close to the line. So we would call this a weaker relationship between x and y. And then here, this is a very weak relationship. They're still kind of clustered in the same general direction, but they're not really close to that line. So here, some but not all of the variation is explained by the variation in x, or some but not all of the variation is explained by my linear model. Okay, so here, this is when r squared equals 0. This means there's no linear relationship between x and y. So one way to think about this is my slope is 0, so nothing's going to happen to y as x changes. So none of the variation in y is explained by the variation in x. So remember how back in chapter 4 we talked about how the standard deviation of a large sampling distribution is called a standard error? So that's what we're talking about now. So here the standard deviation of the variation of observations around the regression line is estimated by this, where I have a standard error equal to my sum of squares error over n, which is my sample size, minus 2. So we have to calculate our sum of squares error first, and that would then just be divided by n minus 2. We can then move on to find the standard error of the regression coefficients one at a time. So the standard error of my slope can be found this way, where I have sigma squared hat, so the predicted variance, all over the observed x minus my average x quantity squared, and then all of those summed together. And then the standard error of my y-intercept can be found with this formula. So they kind of look big and ugly, but we'll get to some ways to make it faster in a minute. So where sigma squared itself equals all of this mess, or simply put, the sum of squares error divided by n minus 2. Okay, so one way to visualize my standard error, what that means, if you remember, where my standard error just means how far away something is from my mean. So kind of like how many standard deviations it is from my mean. Same idea. So here, my variation of my observed y values from the regression line would be this many standard errors. So here, if I have a small standard error, this is what my regression line would look like. So the values are pretty close to that linear model. Here, if I have a large standard error, that means those values are not very close or not very centered around my linear model. This over here then would be the standard error of my slope of my regression line. So notice here, if I have this middle one is my predicted slope, or my y hat, these values right here would approximate a small standard error of the slope, meaning the slope could be this value right here or this value right here, but it's not going to stray or vary too much from the one that I predicted. This one down here then would be a large standard error of my slope, or those slopes would vary or those slopes could be pretty different from the one that I predicted.